I want to try something new and go over a paper I read regarding this famous effect of quantum mechanics, the Aharonov-Bohm effect, which is regarding how the vector and scalar potentials of the magnetic and electric field affect charged particles, even though the field itself might be zero. And ever since I first saw this back as an undergrad, I was always fascinated about it. And this paper did nothing to help ease that fascination. In fact, it made me want to dive in more, especially in the interpretation of some of these effects and the authors that wrote back to AB's original paper back in the 60s. As you can see, this paper was dated back to the 70s, and it's still of discussion today. So that's pretty cool. And, the overview of this paper is basically a gigantic lit review post when AB made the publishment on their effect. And so we'll go ahead and highlight some key points there and see what is actually going on, or try to anyways. Again, we'll take this as a trial run because there are plenty of papers to look at and a lot of fun to gain from them. First thing I think here is that what we need to realize is that this effect is in the regions where the electromagnetic field is non-existent. Classically, we know that makes no sense because in classical mechanics and in all the other classical theories, it was that the fields did the work or changed the particle's motion versus something else. So the fact that we're still having an interference with a particle, even though the field is zero, is kind of weird. And in fact, a lot of other quantum mechanic effects and pedagogies that were looked upon as far as the thought process came in the early 1900s and then in the late 1900s. Things like EPR. That was another big one. That just the theory there was one where we had action at a distance, and that brought into the concept of locality versus non-locality. And that's going to be a big thing here where we have this concept of absence of action at a distance, which is all over the place in this theory. And we'll see later is that we can kind of define what locality means. And I think it might even be better to start with that in some senses because that's one of the big hang-ups on this. But what this author does is he goes through a very good review of several of the then published papers and what their statements were, and then what AB responded to with their effect. But to start off, what is the effective question here? He gives an overview in section 1 of what it is, knowing that we have in here a Hamiltonian that is regarded as the energy, where we have the kinetic term here, the potential, all that fun stuff. In the quantum case, we go to the canonical momentum, things of that nature. Here, we see if that we want to interact with the electromagnetic systems, we have to include the vector potential and the scalar potential. So here A, that vector potential, phi, the scalar potential, which we know this is related, the vector is related to the magnetic field, and the scalar is related to the electric field. So pretty easy there. We then move on to the construction of it, how it works with respect to the fields and what are the expected outcomes. Here, of course, after studying electrodynamics, you know that B is the curl of A. But from the curl of A, we dive into the fact that you can get the same B field from several different A's. Okay, so this leads us to the concept of gauge transformations. And of course, you couple that with the scalar potential, which of course we know the gradient or the curl of a gradient is zero. So we have all these things coupling together to create a gauge transformation. And one thing to note here for gauge transformations is that the gauge transformations result only in a phase shifted wave function, so that this is untouched. And we saw, at least in Griffiths, quickly on that regardless of whatever the phase is, the probability density, which is the observable phenomena, stays invariant because of the complex nature and the complex conjugates canceling one another. So pretty cool there. So a lot of mathematical background on everything. Nothing too crazy if you had a little experience. Some of the math might be a little spooky if you haven't seen it before, but what is needed to be highlighted here again, though, is that AB pointed out that the phase factor, right, could lead to physical effects even if the charged particles moved in only field-free regions. Because the phase factor had this, which we talked about how soon with Stokes' theorem and such, that the Stokes' theorem brings back to the magnetic field, and because of that, we know we have a zero field there, so we still have an effect that's measurable or that's there, even though the magnetic field is not, so we cancel out. Let me scroll to that. We cancel out what's going on thanks to Stokes' theorem. Yeah, so that's in equation 16. Now, what's important to what I didn't really take into account the first time I saw it, I'm sure it was presented to me like it was presented to many of you from a Griffiths book, and they only encountered they only showcased the magnetic and the vector potential picture of it. In this paper, they actually have the magnetic AB effect and the electric AB effect. And this is the basic picture of the magnetic effect, where we have a solenoid in the middle, and we know that the field of a solenoid on the outside is zero. The field is concentrated in the middle, so concentrated here. And here we have just the beam, which they can go path 2, path 1, but eventually they come back to the point P and recombine. At point P, they have a shifted wave function, or rather the phase shifts add together, and that does lead to some unique stuff here, because when they recombine, if we assume that linearity still holds because quantum mechanics, we see that the probability density of the electron is now psi star psi. They have the basic terms here, but they also have the cross terms, and that does lead to a physically observable effect. So we see a phase difference has impacted its or made its effects known on the observables. That's pretty cool. Something you would not have expected, because classically the electromagnetic field matter because they are what change the dynamics of the particle. But quantumly, it's the potentials because of this Hamiltonian construction that we have leading to this phase shift that is going to be what we have to deal with later. And that's just something I was like, that's odd to think about, but kind of in hindsight, we have the grace, and hindsight allows us to have the graciousness to move with that. I also find it really funny that this effect is known as the AB effect, right? But yet they're talking about the vector potential and the magnetic effect and the magnetic field, both AB. So at least now you'll never forget that AB belongs with AB. I didn't realize that until this paper, but that's kind of funny. So moving on, we see here that now we talk about that was the magnetic case, but there's also an electric case where we could send things with a time variant potential, scalar potential, here and here. Instead of a solenoid, we pass the beams through Faraday cages to block out any external fields. That's a pretty cool system that I, again, was not presented with initially, but still fair enough. And it was really cool to see that, again, these come back to the same effect, although we have a zero field. And in fact, as highlighted here, we see that the two scalar potentials and the two Faraday cages are the agents for the physical effect, which are demonstrated in the interference at P. So when they recombine at P, they have this interference, which we kind of saw with the cross terms last time. And that's just really weird to consider when we're talking about quantum mechanics, because the fields are normally what did the stuff, did any change in dynamics, and now it's all the potentials. So now we have to deal with a philosophical question of, is this a matter of locality or non-locality? And later in the paper, they talk about our perceived bias towards it. I'm going to probably have to zoom through the literature stuff because I think it's best to get through the point of the paper. But here, the elaboration of the AB effect, they talk about two categories of paper. Those that were trying to showcase that they fit in with the Heisenberg uncertainty principle, and those that were trying to say, well, look, you're not actually showcasing everything. You don't actually need the potentials. You need the fields themselves. And then the author goes into how some of these pages or papers try to dispute the effect of the potentials, and then shows a good back and forth between AB and the authors that try to criticize their original work. Pretty cool, I must say. And if you want this paper, just I guess send a message or comment, and then we could exchange some way of getting you the paper. Probably email since it's a PDF. But pretty cool. And in fact, a lot of these papers from other scientists actually confirmed the AB effect with a couple other methods. And I found that this, who was also supporting author, the author who made these figures, also decided to be like, all right, well, this clearly fits into the uncertainty picture, and devised a way to show that with these diagrams here. Again, feel free to read up on it because it is pretty cool to see how they detected that. And, you know, this fits in with what we had just covered in Griffiths with angular momentum, because in the paper they find that you see my highlights here, the influence the allowed values of the energy and angular momentum of the electrons without inquiring into the mechanism of this influence. So we didn't need necessarily the fields, although we knew that we had these potentials lined up here, field here, superconductor there, all this other fun stuff here, capacitor, and it was just the Faraday cages, and it was just really cool to read through how they kind of dissected this. Again, with the time frame being back in the 60s and 70s, this is pretty cool to kind of dive back into. I'm sure you could see by the typeset that this is pretty difficult. Some other physical things that I took away from this paper were the arguments of the single valuedness of the wave function, although not directly correlated, but still kind of cool. The wave functions must be single valued, even in multiply connected regions. So that was kind of weird to consider, but then a paper that you should look into later that was also mentioned in Griffith's book by Merzbacher. I'm probably not pronouncing that right, but he concludes that you can have a single valuedness with the AB effect. So that's pretty cool to see. Was not expecting that at all. Now, going back to the second column here, here is where we see a dispute with regards to the actual effects. And DeWitt here tries to show that you can reformulate the potentials by using line integrals and just getting the field itself. So, you know, that didn't hold much merit, as we found out a little later, but still an interesting way. And what I would say is it's good to see past arguments so that we can gain insights and do maybe our own perceived biases. I know that I didn't pay attention to some things that I should have earlier, and it's just you can still gain insight from reading some of these back and forth. So thank you, Herman, for putting this together, because I had no clue there was so much back and forth on this, but with an effect as theoretically, you know, not so clear and concise, especially in the realm of locality, given EPR and all that other stuff. This had a lot more to deal with than what was maybe originally thought of, or definitely more than what we see in an Introduction to Quantum Mechanics book. So there's a lot more that goes behind every one of these books, plus the authors and their patience, because it is difficult. One day I will write my own, but I need to get a little more dirty in these papers first. little more background, get my hands dirty. But nonetheless, we see that we kind of end up back in the same result that AB originally posed, just in a different language. To which DeWitt and company go through gauge invariant wave functions are not actually gauge invariant. And so you see that we just have a lot to deal with, and the language that we use to choose is very particular, in that it's more of a metaphysical conversation now, but it all kind of baffles down to this non-local argument that he has summarized. Here's something that they said, as I believe he summarizes his paper for DeWitt. It's pretty cool because we can see here that we have a couple of options. 1, 2, 3, and then we see what we have, or excuse me, 3 right there. We see that choices 2 and 3 avoid the non-physical annexes to the Hilbert space and allow the actual observables as a complete set of commuting variables alpha. Versus some other possibility of 1, 2, and 3, however, it's largely a question of convenience. And again, when we're talking about the metaphysical construction of a lot of these things, it is definitely difficult to wrap your head around because a lot of it is talked in a language that we may not have on the ground level quite yet, but still a fun thought experiment. That's why Einstein in the early 90s had such a fun time with these thought experiments, and it definitely paid off with high marks for him. Everyone remembers his name now. So yeah, in this little section, we see that for section 3, further work by A and B, they published some responses to the other papers, which were starting to come in flusters, and a lot more turbulence was starting to uproar. Again, it's baffling to me that we have a paper from the 1959 still being talked about and discussed to this day. Pretty cool, in my opinion. Yeah, so let's get back to what we actually need to here for the significance of this. And again, I will send this paper out to anybody who wants it. But this is the back and forth that A and B had with all their other papers that were published with them or against them, and just comments in general, which again, definitely some cool stuff. Highlight here a couple key points. Seems like in one discussion, the concept of force is, in quantum mechanics or quantum theory, an abstraction of secondary importance. And that was our whole point in the classical theories, which was to gain an insight on the dynamics so that we could find a trajectory. Because from F equals ma, once we find A, then we could use our math to find x of t and find out what the trajectory was. Ideally, of course. Here, there's also, in the other chat, or the other response, they had the principle of localizability, which brings into the physical sense of the geometry, is in fact playing an important role. And so we can't just say that everything was discovered based on data and experiment. Some of these things were hypothesized. There was no way for Newton to be able to collect all the data necessary with the tools of his time. So these concepts of letting math kind of guide us to a point where we can then look for data to support what the math showed and starting to take over. Look at what Higgs did with the CERN experiment out there in Switzerland. Amazing work, but that all kind of came from a kind of weird theoretical framework where things are fitting together. So that is one of the points highlighted in this last response. And it does not change color. And then where we say that are determined simply from experiment alone, that is not always the case here. Mathematical forms do play a role. So pretty cool, but here, this section and section 4, I feel, is the point that all of this is trying to highlight and that is that we have a really kind of metaphysical question with this. Here, the author states, firstly, the AB effect emphasizes that the force, which we kind of touched on earlier, concept is so central in classical physics, plays a very minor role, if anything at all, in the structure of quantum physics. Again, we have to change our whole perspective now because that's what we were trying to understand in the first place for so many years. And it's not always easy to undo what we first thought. So he talks a little bit more about that here, things like that, in Newton, Maxwell, and all those other experimental phenomena. So then we get to the second point that the author wishes to highlight, which is the question of AB effect discussions, that of the localizability principle in physical theory. Again, this is the intuitive tendency to prefer local theories versus non-local ones. And so we kind of have to get rid of ourselves because, and I like this definition of what it means to be local, where it says, perhaps this is an expression of our common experience, that is, the cause has to be where the effect is. Cause has to be where the effect is. Localizability. So, thus, action at a distance seems to be a violence to our normal thinking patterns. And, I don't know if this is an actual parallel analogy, but when we're looking at physical therapies, things like that for sports injuries, sometimes where the symptom is, the cause isn't always there. We have to look up the kinetic chain as well. And to me, this seems to be another kind of fill in that because, again, the fields used to make the change in the particle. Now it's something else. And if there's no field, then there should be no change, but there is a change. So this concept of action at a distance, via the fact that the potentials had no physical meaning in electrodynamics, now have a big importance to the theory that's coming together. And then later they talk about, zoom down a little bit. So here they now talk about kind of a metaphysical picture difference where fields are present. The total physical picture is different from that which is obtained when the fields are absent. So now we're not only looking at a kind of weird microsystem, but something completely global to the system itself. And then we try to reframe it. This guy here, let me scroll up. Where's his name? Yes. So Herman outlines how this physicist tries to reconstruct this in a framework, not necessarily an interpretation work, but in a framework to where we have a different analysis altogether, and the force does matter. But in the end, it's not really there. It would be on this scientist to prove it, since he's the one making the assertion. And that's not really easy to do with the exchange energy that we see here in equation 23. So a lot going on that I just didn't have any idea was even there to start with, but pretty nice to see coming in full effect. So then we finally make it to the end where we look at, again, we're just saying that they indicated that the AB effect could possibly be explained within the framework of a localizability of the physical effects principle. And again, this is just trying to assert something that may not be actually there with the causal role of the electromagnetic potentials. So this seems to be more of a metaphysical argument and a language argument than it is the actual physical assertion of the effect itself. And so we finally conclude there that there are physical effects on charged particles in regions where they are free of electromagnetic fields. And so we have to now ask ourselves, to which perspective do we want to keep holding? Do we want to hold on to this localization, or do we want to have non-local theories, to which the likes of Einstein Newton and others hinted towards beforehand, but aren't necessarily there yet. And finally, let's go to this part here. We see that the question of the localization or localizability of physical effects raised by AB is just such a question of the metaphysical principle to be answered by the future direction of physical theory. And even that it's been raised back then, we kind of see that this metaphysical picture or metaphysical question is still being used now in the likes of any theoretical physics, string theory, and several others that just keep coming together. I'm sure there are many other different approaches to this paper and insights. Again, I would love to have a discussion if someone else would like to read it as well. I am just fascinated that they came up with all of these in the time frame that they did. And it's really cool that this professor who wrote this paper also had an exchange with David Bohm himself, and they had a back and forth on the language used by it. And I'll go ahead and let you all read it if you'd like. If not, again, I'll send you the paper, but it is pretty cool to see the exchange that used to be there. And it almost seems like with the quick responsiveness that we have now, there's a lot of weirdness going on in publications regarding wanting to publish only positive effects when negative effects can still be useful to several in the research space. So with that, we will go ahead and conclude this. Woo! Still don't know what I'm doing yet, but this was kind of fun to look through. If you have a suggestion for a paper, please tell me, because there are so many to choose from. But this was one of those I had an intrinsic curiosity for, and now I'm even more curious, so we will try this again. It's pretty fun.